Independent and dependent probabilities is an important topic on the ACT. It's probably the most frequently tested probability topic. So there's two ways things can work. Either each trial, each thing can have no effect on the other, or it can change as you go on. Let's look at compound probabilities, which is independent events occurring. So let's say we flip a coin twice, and we want to know what the likelihood of it is coming up heads and heads. Here's where people goof up. They think you should add here. No. Because if you add, you get 1/2 plus 1/2 equals 1. That means it's a 100% chance that you'll have heads and heads. Multiply. 1 times 1 is 1. 2 times 2 is 4. 1 out of 4. That makes sense. Let's look at it. So our first flip can end up heads or tails. Then our second flip can end up heads or tails. Heads or tails. Now, there's 4 little universes right there. And only in one of the 1, 2, 3, 4 does that happen. So always multiply. Always multiply with probabilities. So let's take a look at the example at the bottom of your screen. Again, it's kind of text heavy. You can expect that on that sort of problem. They left the answer choices in terms of fractions. Again, fairly common. John's rolling 3 6-sided dice and needs to get 6s in all 3 rolls. Now, it doesn't matter that he's rolling them all at the same time. It doesn't have to be one after another. Each dice is independent of one another. So he needs 6s. That means he needs a definite outcome on all 3 of these things. So his likelihood of getting there, his chance of getting there will be 1/6 times 1/6 times 1/6. 1 over 216. Why? Well, he's got a 1 in 6 shot of rolling 1/6. He's got a 1 in 6 times 6, 36 shot of rolling 2 6s. And it turns into 216. It's just very unlikely. It's very unlikely. As the number of events goes up, for example, if I had 5 coin flips, the chances of getting heads gets really, really low, right? It gets to 1 in 32. As the number of events goes up, if you want specific outcomes, the probability will decrease really quickly. Because remember, the most probability can ever be is 1. Essentially, you're always going to be multiplying fractions that are less than 1 with fractions that are less than 1. So they're just going to get smaller and smaller. So the other way this works is dependent probability. So you'll see I put a new question in the bottom corner. There are 10 cards in a deck. 4 of them are blue and 6 of them are red. Jimmy draws a card and then without replacing draws a second. So what are the likelihood that he draws 2 blues? What is the likelihood? So in this example, the probability changes from the first card to the second card. Why? Because Jimmy doesn't put the card back in. If he puts the card back in, it's just like the dice example or flipping coins. The probability is the probability is the probability. But because he does not put the card back in, that probability will change. So his first card being blue, well, it's what you want over everything you got. He's got a 4 in 10 chance, you could say 2/10 or 2/5, but I'm not going to reduce that just now, of getting the blue card. Now, let's move this down here just for 1 second. He's taken a blue card out. There's not a blue card in that deck, and he's not putting it back in. Now, people make 1 of 2 mistakes here. They either subtract 1 card from the bottom, from the deck, and not 1 from the blues, or 1 from the blues and not 1 from the deck. You have to do both, right? Because the deck doesn't have 10 cards anymore, it has 9. Because 1 blue card is gone, there aren't 4 blue cards anymore, there are 3. So the new probability is 3 over 9. And that may make sense to you too. If you look at this is a 40% probability, right? 4 over 10. This is a 1/3 probability, 33%. So the probability will diminish. And then it should, right? Because, we only took 1 out of 10 cards away, but we took 1 out of the 4 blue cards away. So there should be less of a chance. And to finish the problem, we just multiply these together. 12 over 90. Of course, that'll reduce because we have 2 evens. We could also reduce it by 3 since they're both divisible by 3. And we could say this is 6 over 45. Or we could say this is what? 2 over 15. So 2 over 15. Not incredibly likely he'll be able to do that, somewhat less than a 20% chance. So there's one other thing I want to talk about. This goes back to the realm of independent probabilities, but it can show up here as well. So let's say that they give you a question that says, Jimmy rolls a dice and he wants his second roll of the dice to match his first. What are the odds of that happening? Well, a lot of times I'll get this as an answer. 1/6 times 1/6, and people will think that's right because, well, he wants the rolls to match, right? So isn't there a 1 in 6 chance that that'll happen on the first and the second roll? Actually, no. It doesn't matter what he rolls first. It could be a 1, 2, 3, 4, 5, or 6. That's irrelevant. All that matters is what he rolls the second time and if it matches. So if he rolls a 2 the first time, there's a 1 in 6 chance he'll roll a 2 next time. If he rolls a 4, there's a 1 in 6 chance he rolls a 4. So be careful of that. It's a classic little trick that they use from time to time. Okay, our last probability video talks about expected probabilities. This is a newer topic, didn't used to show up on the ACT at all. And really take a look at it because it shows up pretty frequently in this new Red Book.